Hi, welcome back. So, let us continue using the momentum equation. Now, here, so let me draw an axis. So, this is what we were doing, right? And you have this flat plate which is DEF, right? And we have taken a control volume around this which starts from basically A, and it runs just inside a streamline which is very far away from the flat plate, right. Essentially this streamline is looking at free stream. So, we draw a boundary just inside that streamline, so which is AB. We come down and we run far enough, right, on the outside of the flat plate, right, like on the downstream side. We go far enough and we come down by C. We make this cut right here at C, so that we can run back to the flat plate, run over the surface and wrap ourselves around the flat plate, come on F, come here back at G, which is right exactly below C where we had begun the cut, and then we come down again H and again run along just inside another streamline which is very far away from the body, and we go back and we close the volume. So, basically we have a control volume, right, which is A, B, C, D, E, F, G, H, I, A, right. So, we go from, as you see, we go from A, we go straight down here to B, we come down to C, right, we go along D, right, and then we walk along the surface like that, touch the surface completely, then go back here at G, come down, go inside this free stream surface, and then go back to A. So, that essentially is my control volume. Okay? And the axis system that I am looking at is something like this, right. So, let us say this is x and this is y, of course, right. So, as we know from our experience so far that we have taken basically two sections, right, 1 and 2, and u1 is constant, right. So, basically what you are saying is u1 is constant while u2 is a function of y. So, I think this is something that we kind of used to now, right. So, now what is interesting is the way we would like to calculate drag is basically look at surface forces on the control volume, right. So, in order to, because that is our purpose here, we want to evaluate drag. So, what we are going to look at is surface forces, right, surface forces on the control volume, right. So, in order to do that, so let us sort of go and do that. So, number 1, okay, it will come from, there are two things here, okay. So, that basically will come from pressure distribution on ABHI, right. What does that mean? So, when I say pressure distribution on ABHI, so AB is essentially the top boundary of the control volume, which is just inside the far end streamline, and HI is again the same on the other side. Okay. So, we are looking at the pressure distribution on ABHI. Okay. This, why are we not looking at anything else? Well, we'll just come to that. Okay. And the other thing is, right, surface forces, right, there will be surface forces, right, on DEF, okay, due to the presence of the body, in this case the flat plate. Now, please try to understand here that when I am talking about DEF, I am not talking about the flat plate, I am talking about the control volume, right. The DEF part of the control volume actually wraps around the flat plate. Okay. So, we have taken the control volume in such a way that AB, okay, is just inside or just in sync with a streamline which is far away from the flat plate, right, on the top side, and so is HI on the bottom side. And DEF is that part of the same control volume, right, which is running like a thin skin on top of the and wrapping basically the flat plate, which is the DEF. Okay. Now, what do we need to note here? Okay. So, what we note here is, yeah, so let us sort of write this here. What is our note? Number one, right, the surface shear stress is neglected on AB and HI, right. The surface shear stress, is neglected on AB and HI. Now, why is that? Well, that's because these two boundaries of these two parts of the control volume are far away from the flat plate, right, and there basically it's the free stream, right, and the viscosity effects are negligible, right. So, that's far end. Okay. The second thing is that the cuts that we've made in the control volume CD and GF, right. So, these cuts CD, so CD and GF, okay, are adjacent to each other. Okay. What does that mean? Well, it's basically right side by side of the same length, to each other, such that the shear stress distribution as well as the pressure distribution is equal and opposite, and hence they will cancel each other. Okay. So, this basically means that the shear stress, right, and pressure distribution cancel each other. Let us just say cancel each other, right, because so you can just sort of think about it. I mean, if I were to just quickly do this here, so I could have a pressure, acting like that, and a pressure acting like that, right. So, these two, 1 and 2, that's acting on CD, right, and this say 3 and 4, these are acting on FG. So, these will basically cancel each other out, right. These will basically cancel each other out. Okay. So, they will cancel each other out. So, therefore, cuts, they are adjacent to each other, which essentially means shear stress and pressure distribution cancel each other out. Right. Now, the other thing is that the surface force, now there basically now what we are looking at is this surface force, right. There is this surface force on DEF, right, is basically is the total reaction, right, which is equal and opposite to the okay. Now, on these cuts, however, right, while the shear stress pressure distribution, cancel each other because they're equal and opposite. Now, that is going to cause some kind of surface force on DEF, right. So, on DEF, right, there is going to be a force which is going to be caused by that. So, then when I say surface forces on DEF, it's basically it is basically a reaction, right. It's the total reaction, right, due to the presence of the body. Right. Now, because of the presence of the body, there are surface forces, right. So, here when I write B here, right, when I say surface force in DEF, so due to the presence of the body, so which basically means that this is like it's the complete reaction to the presence of the body. Right. So, and what is the body doing by its presence? Well, it is basically causing surface forces, right, due to shear stress and pressure distribution. Okay. So, what I mean, so okay, if I were to write that, so the surface force, okay, surface force on DEF, right, is the total reaction. This is actually a reaction, right, total reaction equal and opposite to the shear stress and pressure distribution created by the flow over the. So, I am not going to write all of that. Okay. So, it's a total reaction, right, to the shear stress and pressure distribution caused due to the flow of fluid over the surface of the body. So, instead let me just sort of write this down a little bit, so then that will make sense. For example, so what I mean is that I have this surface, right. This is my surface, this is my flat plate. Now, on this, right, I am just drawing at one point just to get this clear, and that and something like this, right. So, this is the shear stress, right. So, this is the shear stress and this is the pressure, right. So, this is being caused, right, this is being caused due to the flow of fluid, right. Now, if I sum all this up, right. So, you can see this. So, I have a pressure and if I sum the effect of both pressure and the shear stress, right. So, I am going to just say that is going to be a reaction, right. It is going to be a reaction, let us just call that as R, right, per unit length. Okay, per unit. So, the depth is into the plane of the paper. So, per unit length, right. So, therefore, my surface force therefore, right, what is my surface force then? So, then my surface force is essentially, right. So, this is the force which is being caused, right, and my surface force or DEF, right, is reacting to this. So, therefore, what that basically means is that there is an equal and opposite. So, this is also exactly equal and opposite to this R. So, this is basically the surface force, okay, on DEF. So, the reason I am trying to say this or dwell on this a little bit is because the surface force consists essentially of pressure forces and shear stress. So, when I do an integration of the pressure and shear stress on the surface, I get a reaction. And the surface force is basically, the magnitude of that is basically equal to that, right. So, that is why this. So, therefore, now that we had talked here, so when I say therefore pressure force here, right, pressure distribution on ABHI. So, ABHI, let us go back here a little bit. So, AB and HI. Okay. So, let me say that I am going to do an integration. So, P and this is ABHI, and I am going to add a minus sign. What does that mean? So, P is basically the distribution of pressure on AB, right. ds is a small element along the part of the control volume, which means I can take a directed vector, right. And why do I have a negative sign? Because you will know that pressure, right. So, this is the ds is basically the vector pointing out of the surface, right. It is the vector in the direction of the area normal. It is like the area normal, and area in this case, so unit depth. So, ds into 1. So, ds is basically unit length. So, ds is the small elemental length along somewhere along AB or HI, and the pressure is always directed opposite to that. So, therefore, you have the negative sign. Okay. So, this is my pressure distribution, and the surface force by this time. So, surface force essentially I can write this as minus R, because this is acting opposite to this R. Okay. So, that essentially is my, so what I am going to therefore write, now is that net surface force, right, is equal to, we just did this, right, A B H I minus R, right. So, this R is essentially over D E F. Okay. So, A B H I and D E F. Okay. So, now what we are going to, of course, we know that rate of change of momentum is basically equal to force. We know that, right. Now, let us therefore, so if I, so these are the net surface forces. Now, if I write from the momentum equation, right, I would request you to just look up the entire momentum equation in case you have forgotten. So, the momentum equation, I would write that as del T, okay, there is a volume integral rho v, this is dV is volume, right, plus this is over a surface v dot this, right, and that is equal to the total surface forces, which is minus R. Okay. Now, of course, we are going to look at a steady state case. So, this is going to go to 0, right, because this is, our case is essentially steady, right. So, therefore, I can write, okay, so therefore, I can write, let me, that R, right, R is equal to okay, minus rho v dot ds of the surface, right, and let me call that as equation 1. Okay. So, that is my reaction. So, now we are basically going to do what the way we have been doing so far, going at each. Now, this equation is a vector equation, as you can see, right. Now, our main objective here was to calculate drag, right. So, this is my, as you can see, this is the total surface force, right. So, what we have been able to, we have been able to get this expression 1, right, using the momentum equation, right, and also understanding that the surface forces is basically resulting as a reaction to the pressure and shear forces. Now, this surface forces when taken component in the x direction, right. So, we have drawn this is my x and this is my y, right. We have taken this as an axis system. So, when I take the component of this reaction along the x, that should be what is going to cause my drag, right. Okay. Okay, I forgot to mention something in terms of the lift. I will go back and mention it. Okay, let me get over this. So, if I take components along the x direction, right, so that gives drag. So, if I do that, what I will get is minus v dot ds, right, into u, right, u is in the x direction, minus right. All this means is that this second integral here, all this means is that you take the component of the pressure in the x direction. You integrate that and take the component of the pressure force in the x direction. Okay. Again, now AB and HI are far away from the body, right. So, which we have already mentioned, right. So, AB, right, and HI are far away from the body, okay, such that, right. So, essentially what we have there is free stream pressure. So, if I do that now, this if you need to convince yourself, if you consult a standard book, you should get that. So, basically this, as long as P is a constant, this integral is going to reduce to 0. Okay, it's going to integrate to 0 as long as P is a constant, and in this case it is, right. So, therefore, what we get here is this also turns out to be 0 because of this reason, that they are far away from the body, and therefore, the pressure there is essentially the free stream pressure. So, what we are left out with essentially is therefore just this, right. So, this is essentially an expression for my drag, right. So, now what we are going to basically look at, okay, what we are basically going to look at is break this down over the several boundaries that we have. Okay. Now, in order to do that, now if you look at this, now let me write that down here. So, each of these points, right. Now, AB, okay, HI and DEF, right, which is wrapping around the body, right, are streamlines of the flow. Right, are basically along the streamlines of the flow, so that what happens to V dot ds? What happens to V dot ds? Right. So, V dot ds, so basically that, right. So, now, if you have the boundary, so if you look at this, if you have the boundary, right. So, ds, right. So, ds is going to be, say, directed somewhere like that, right, and your velocity is directed something like this. So, if you do a dot product, right, so what do you get, right. So, what we get is basically 0, right. So, because so ds is perpendicular to them, right. So, so you can explain yourself. So, therefore, basically this is V ds cos of 90, so which is 0, Okay. So, secondly again, okay, CD and FG, right. So, therefore, from this integral, from this integral here, V dot ds is 0 for AB, HI and DEF, right. Now, again for for the two cuts basically, right. Now, for these two cuts, so CD and FG. Now, what you should see is that the mass flux, right, is equal and opposite. Okay, the mass flux is actually equal and opposite. So, you can whatever comes in here, is going to go out there. So essentially the direction is opposite, right, but the magnitude should be same. The magnitude is essentially same. So therefore, right, now because CD and FG is same, so what happens? So therefore on FG and CD, right, and CD, if you look at this integral, rho V dot ds, right. So this is same in magnitude. Right, but opposite in sign, right. So therefore they kind of, so this is essentially nothing but the mass flux, right. So therefore therefore this also cancels out. Okay. So what therefore we are left out, what therefore we are left out is basically, okay, this. So on the boundaries AI and BH, okay, we're going to do this V dot ds into U, right. So we're going to do this only on these two boundaries. So basically that's what we are left out with, right. So AI and BH, which is essentially, if you see here, if we go back to here, so what we are left out with is AI, right, which is the inlet, and BH is the exit. So if I do that, okay, if I do that, then what I come up with is here minus rho, okay. So V dot ds is minus U1, right. Then this is also essentially U1, okay, U1, and ds is nothing but dy into 1, okay. So similarly, and for this is for AI, this is the inlet, and for this, what we get is rho, okay, and we get U2, okay, into U2, and again dy into 1, right. So if so basically what I'm getting here, so what I get here, okay, is essentially that, so this will come down to rho, okay, U1 square dy, this is over AI, right, plus rho U2 square dy, and this is over BH, right, this is over BH. Okay. Now also, right, also what we get is from, if we do the same thing from continuity, right, from, if I look at continuity, what I get is rho U1 dy minus rho U2 dy. This is on the inlet and this is at the exit is equal to 0. Right. Now, if I multiply by U1, right, throughout, if I do that, okay, if I do that, so then what I get is rho U1 square dy AI is equal, I'm going to take it to the right hand side, is rho U1 u2 dy bh. Okay. So, this is what we get from continuity, and we use this expression. So, we use this expression back into this, right. If I use this expression back there, then what I get as drag is basically, so I am going to replace this by this part, right. So, essentially what I am doing here is this plot is something that I am going to replace by this. Okay. So, if I do that, so what I essentially get is d, and the reason I was able to multiply by u1, because you know u1 is constant, we have sort of proved that before. Okay. So, d is equal to, so then this drag, then I can write that as essentially rho u1 u2 dy, okay, over bh, right, plus rho u2 squared dy over bh, right. Say, or d, right, or d is equal to rho u2 u1 minus u2 dy over bh, right, and this again over bh, this is again equal to, if you see u1 is basically the free stream, and let me just write the u2 as u. Okay. So, then this becomes rho u infinity minus u dy. Okay. So, the density is of course known, right. So, u1 is basically this, which is the free stream, right, and u2 is u, which is a function of y, right. So, this is an expression for d, and what is interesting about this drag, that now you can actually write this drag. Okay, if you look at this, right, if you look at this, that you can write this drag in terms of velocity. There is no connection between this and the boundary layer things that we've learned so far, right. Now, the only relationship, let me just say, is that when we wrote the skin friction drag, right, when we wrote the skin friction drag, and we wrote that as, we wrote the skin friction drag to be, right, for a laminar boundary layer is 1.328 by under root RE chord, right. So, this thing is skin friction drag is nothing but this drag, right, we are going to non-dimensionalize it. So, half rho v square, this is u infinity square, right, this into c into 1. So, this is the dynamic pressure and this is the area, right. Now, this d that you see here is essentially the d that we have just come up with here, right. So, this is laminar flow over a flat plate. So, what you can see here, right, is that now I can actually sort of find out the drag, and hence the coefficient of friction, if I have some idea about the flow, this velocity profile at the exit, right. So, we could do a little, small little thing, a small little problem, before we start the next module. So, I will just stop here and kind of do that in the next module. Okay. So, essentially what we have done here, and I will talk a little bit briefly about the usefulness of this. Okay. So, it's basically the same, we have got an expression for the drag in terms of the free stream and the velocity at the exit, okay, which is something that is easy to measure. Okay. At least that is something I can measure, and this is the same drag you use to calculate the skin friction coefficient. Okay. So, I will stop here and we will continue this again from next class. So, thank you.